Okay, last time this is where we stopped. We were talking about. Remember, we are talking about. Let me start from the beginning, maybe. Okay, this is about file systems, chapter number 4. In our discussion of the operating systems, we said that so far we have abstracted two main concepts in the operating system. One is the processes, which is about CPU. The other one is the address spaces, which is about the memory. Now we are going to look at the secondary storage, and our new abstraction concept is the file. We talked about it, and by definition, it is as simple as the idea of process and the address spaces. It is simple, but as you know, I mean, the simple things, when you go into the details, they turn out to be not that simple anymore. That's what we are looking at with this chapter. We looked at these definitions. First, we looked at how we use files as the users. I don't need the zoom. Okay. Okay, so first we looked at how we use these files, the idea of the files, then the directories, and etc. Then we started looking at. For example, this program is a program that copies one file to another file. As a user, how we do it. As a customer of the operating system, how we do it. An example. Then we started talking about file system implementation, right? That was the main thing that we were discussing last time. With the file system implementation, we first looked at what happens when you boot your computer. Okay, what happens when you boot computer is a different discussion. We are talking about the prospects of operating system booting up with respect to file system layout, and we talked about master boot record and the partition table and the active partition and etc. And depending on your partition type, depending on your file system type, your partition of course changes. For example, this looks like a Unix-based inode system. In the first one, it could be an NTFS system. In the third one, it could be a FAT-based system. Depends on the partition type. That's what we looked at. And we said that whatever your file system is, you need to store your files in your disk. So what are you gonna do? Either you are gonna use this contiguous layout. We talked about it. We said that we like it because it is very simple. You just contiguously, store your files one after the other one, no space between them. The problems appear when you delete some of the files and you get the fragmentation issue. You have 5 blocks free here, 6 blocks free there, but I cannot fit total of 11 blocks free, but I cannot fit a file of 10 block length. So that was a problem. So we needed the compaction and that kind of stuff. That's why we said that people don't use this much other than the CD-ROMs, because in CD-ROMs there is no modification of a file or there is no deletion of a file. So the CD-ROMs uses this contiguous layout. We looked at that one. Okay, and then the alternative would be the linked file allocation. It's just each block of the file is just linked. Okay, linked list. You start from the beginning and you follow the links, just like the regular linked list, but it is implemented on your secondary storage. And we said that this is good. There is no external fragmentation. The problem is sequential access is slow. Random access is way more slower. So what are you gonna do? We said that maybe keep this linked list in the memory. Then you have invented this file access table mechanisms, FAT mechanisms. If you keep this table in the memory, that's good. You don't have to traverse all the nodes on the disk one by one, because you are doing the traversal stuff in your memory, and memory is thousands of, sometimes millions of times faster than your disk. So this is not going to be a very big problem in terms of speed, but this file gets very big. This file access table gets very big. Sometimes it is bigger than your main memory, and I don't want to do that. So that was the problem. Then we have invented this index allocation. It's like the file access table, but for each file you have a inode index node, okay, and you keep that in your memory when the file is opened. Otherwise, you keep these nodes, inodes on the disk, okay. And since these inodes, index nodes, those are special blocks, are special. You keep them in special place on your disk surface, a place where the access is is faster than the others, and this becomes your inode based file system. Unix uses from the beginning of the Unix days, from 60s, 70s, it uses this inode based file system. Okay, so we talked about these, then we talked about how we implemented directories. I am going to skip these because these are kind of details, and the shared files, and you remember the linking stuff, hard linking and soft linking. We looked at the details of those and the problems that they may create, and I think that was it, and we stop at this point. Are there any questions? So these are your faces. Okay, good. Okay, so let's continue. Log file systems. Okay, so the idea is this. Are disk drives, okay, whether they are mechanical disk drives or the secondary solid state drives, doesn't matter, they get faster and faster, okay, but our CPUs is way more faster, and we have large amounts of cache memory. Between our secondary storage and our computer system. That means what? I can keep lots of this data. The picture looks like this, okay? It looks like this. This is our CPU. It is connected to my secondary storage, a disk or solid state drive, doesn't matter, through the controller, right? This controller has, okay, gigabytes of memory in it. Okay, 2 gigabytes of memory in it as a cache memory. So it can hold lots of data. The principle of locality is valid between your CPU and secondary storage too, because I mean, if I am reading a file, usually I am going to read the next part of the file. So the idea is, if I keep that file in my cache inside this controller, most of the time I won't do any disk access. So my I/O will be very fast. So along with the developments with this cache management algorithms, our reads becomes very efficient. The problem becomes the writings. Okay, when you try to write to this cache, and if you don't write it to the disk, then that's a problem. Why? Because if there is a system crash, then you lose that data. So most of the time, okay, you try to write your stuff back to the disk more frequently, because you read it once, but you have to write it many times. So some people said that if most of the time I am writing to the disk, but really reading from the disk, maybe I should do this. Okay, most future accesses will be writes. So the read ahead mechanism used in some file systems to fetch blocks. Yeah, I know this. So all writes are initially buffered in memory, inside this memory, or some memory, my memory main memory unit. Okay, periodically all the buffer writes are written to the disk as a single segment. Okay, so you are saying that I am not going to write this to the original places, but I am going to write these as a single segment to some part of the disk. So that means what? That means you are going to fragment all of your files. That means you are going to change your file system structure a lot, but this is going to make your life, this is going to make your disk access speeds improve a lot. Why? Because you are writing all of your stuff to the disk at the same time without doing any seeks or rotational delays and etc. Those are called log file systems. They say that I am reading most of my file stuff from the cache anyway, but writes, I have to do the writes. Periodically, I have to do the writes. I cannot wait indefinitely to write a dirty cache unit. So what am I going to do? I am going to write all the dirty blocks to the disk at the same time to the same disk position. So to the same disk segment without doing any seeks or rotational delays. Well, that's going to make your file system a lot complicated, but the advantage is your writes will be very fast. Okay, and you are going to write to the disk periodically when the system is idle. So it looks like your secondary storage is behaving something like a second kind of memory, right? Like a second kind of, a little bit slower memory, because most of the time you are processing your data from this controller, okay, or some part of your main memory, and that will be very efficient. The cost is your file system will be more complicated. So those are called log file systems, okay. Another file system type is this journaling file systems. In journaling file systems, again, the problem is the crashes. Okay. So when your computer system crashes or your operating system crashes, previously when we consider the processes and the memory, we can't do anything about the recovery. Okay. Once the system is crashed, you cannot recover your data because your memory is lost, your CPU content is gone. But with the file system, the things are different because, I mean, you cannot give up your data on your disk. It is important. That's the idea of disk actually, okay? Remember what we said at the beginning? We said that we need some space, we need some mechanism of storing long-term information, right? Long-term information without any worries about losing that data. But the thing is this, while I am doing some stuff on my desk, if the system crashes, power goes out, something else happens, a mechanical stuff can happen, I don't know what happens, something happened, and my system crashed, and that might put my whole file system in an unstable situation, and that's not going to be good. Let's look at this example. For example, this is how you remove a file in Unix. Just delete a file in Unix. This is what you're going to do. Remember, files are pointed in their directories. Okay, files are pointed in their directories. So I remove the file from the directory. I am not done. That file has lots of inodes. So I need to release all those inodes to the free inodes list. And then by scanning those inodes, I need to return all the disk blocks to the pool of free disk blocks. Okay. So these looks nice, but it's going to take some time to execute all of this stuff. So what am I going to do? I'm going to execute them. But the problem is, what happens if there is a crash here? After removing the file from its directory, I did not release all the inodes. That's a problem, and I did not release all the blocks. That's a problem. And what happens? There is a crash there. I released the inode, but I didn't release the disk blocks and etc. So as you see, anytime I have a crash during the execution of these algorithm steps, there will be some instability in my file system, and I don't like that, because if I keep doing this, most of my disk will be unusable. I keep deleting stuff. I am not returning inodes. The worst thing is that I may end up using the same inode for two different files, and that will be a corrupted file system. Okay, so that will be a problem. So what are we gonna do? This is where the journaling file system idea comes in. Okay, it says that whenever you are going to do something with your secondary storage file system, you keep a journal. Okay, you say that I am going to do this, this, and this. Okay, you tell the system what you are going to do first. So I am going to do these 3 things. 1, 2, 3. Now I am going to do the first one, I am done. Second one, I am done. Third one, I am done. This way, when the system crashes at this point, okay, when you boot up your computer again, the file system knows that you plan to do these 3 steps, but you have completed only 1. You can continue doing the second and the third one, or you can undo the first one, okay? Because you made your intention known before you started doing these 3 stuff, okay? So you are kind of keeping a journal, okay? Like the journals of those big ships, their captains, they always keep their journals. They say that this is our plan. I am going to do this and this and this, and after execution each step, I did this and this and this and that. So if something happens, they go back and they look at that journal book, and see what happened in the past. That's kind of what is happening. Or those black boxes of the airplanes, remember those? So you keep a record of what you did and what your plan is. Okay, those are called journaling file systems. And our modern operating systems and the file systems, for example, the Linux's exe3 or the Microsoft's most popular one, NTFS, is this kind of a file system. So they are kind of robust against these kind of crashes. Okay, robust against these kind of crashes. Those are called journaling file systems. Okay. So when I say a journaling file system or log file system, these are kind of ideas, right? So your file system can implement both this log file system idea and the journaling file system idea and some other idea too. So you should not classify a file system like a journaling file system or the log file system. These are just concepts, these are just ideas, and you can use these ideas in your file systems too. Okay, any questions? Good. This is the journaling file system idea. Another file system idea that we use very often is the virtual file systems. Okay. In many cases, on a simple computer, as simple as this computer, you end up using more than one file system. Okay. For example, in Windows, I usually have one main disk, an SSD usually, but if you insert a USB drive, the file system of the USB drive might be a different one. Okay. For example, you have formatted your USB disk on a Unix terminal, so it has ext3 file system in it. You inserted your USB disk to your Windows file system, so your C drive has the NTFS file system, but your D drive has the ext3 file system. But whenever I open an Explorer like this, Explorer shows me these files like a regular Windows file. So when I say give me the attributes of this one, it gives me the attributes of those. Okay, it doesn't care if this file is from a FAT file system or NTFS file system or an ext file system. So how does this happen? Let me try to launch this one. Yeah, okay, good. Yeah, okay. So this is a very crude approximation of the Linux operating system, as you know. But since this is Linux, okay, this one thinks that all these files are inode-based files. So when I say give me the properties of this one, it says that okay, these are the owners and these are the read-write permissions for the user and the group and the others and the last access time and etc. Right? So this interface thinks that okay, this file belongs to an inode-based inode based file system. But in fact, I know that this file is stored on my C drive, and my C drive is formatted as an NTFS file system. How does it happen? So that's the idea of the virtual file systems. Okay, this is what happens. Okay, there is a virtual file system available, and this virtual file system, under it there are real file systems. For example, an NTFS file system, an ext file system, or some other file system. And whenever I try to, for example, issue a POSIX based file operation such as open file or give me the file attributes, okay, this virtual file system translates all these operations to the destination real file system. And this destination real file system does whatever it needs to do. Okay, that's what is happening here. When I say give me the attributes of this file, like a regular inode based file system file, okay, so it gives this issue to that virtual file system, and virtual file system translates all these POSIX based file operations to the NTFS based file operations. Those are called virtual file systems. Let me, okay. Does it work this way? Yeah, I think it should. No, it is not. What was the name of it? Windows Explorer? It was. What was the name again? I used to do it. I think I did it a few times. I forget the name. What was the name for the Windows Explorer? Explore? Yeah, maybe. Yep. Expand Explorer.exe. Yes, that's correct. Explorer.exe. Okay, good. It's running. So when it runs, okay, now this is giving me the Windows view of my ext3 file system. It looks like it shows a pseudo network. Okay, with the pseudo network, my file system is like a network file system, but in fact I know that these files are stored on my C drive. So this is actually the picture of the virtual file system I am looking at, right? This is what I am looking at. So I say that I am looking at a network file system, but in fact I know that it is not on the network. It is on my desk. This is how they cheated. This is how they implemented their virtual file system. Okay, everything is stored on my NTFS, and I think this is NTFS, right? Let's look at that one. So where are my NTFS? Yeah, it is NTFS. So all of my files are stored in an NTFS system, but because of this virtual file system, network-based virtual file system, I see it as an inode-based file system. That's what the virtual file systems are. And the implementation is as simple as this. For example, I am trying to show you a POSIX-based file system. Okay. Of course, I have my process table. And remember, in your process table, you have a pointer for your open files. Remember the process tables? You have all the accounting information about your processes, your memory, and that kind of stuff. With your process table, okay, you keep a pointer to your files, open files, file descriptor tables, and inside these file descriptor tables, you have a pointer to your vnodes. Okay, vnodes are kind of inodes, but these are virtual nodes. Okay, inside these virtual nodes, you have function pointers for opening files, reading files, writing files, and how many operations you have for the disks. You have all those pointers to those. So it doesn't matter actually what kind of file system you are using. you keep changing your pointers from one function set to another function set. So whenever I like to open a file in my virtual file system, it opens the file in the real file system by using this translation table. It looks like polymorphism. It is exactly like polymorphism. Why? Because I just say open. I don't know what's going on underneath. It is doing some kind of a translation during runtime. It's a little bit slow, but since, I mean, in the disk world, in the secondary storage world, the meaning of slow is a little bit different, right? Because, I mean, if you are going to make a disk access, that's thousands of times slower than your memory stuff. So I can do thousands of things in my memory, in my CPU. I am still not that slow because the alternative is going to the disk. Or I'm going to do the disk anyway, so I'm going to be thousands of times slower than the memory. So why does it matter to add a few microseconds to it? Microseconds in the CPU world and the memory world are very, very long times, but microseconds in the secondary storage world is not that big. Okay, so I can afford to do this kind of virtual file systems if I like. Okay, good. Any questions? Where is my attendance sheet? Okay. Good. So these are the virtual file systems again. I mean, we have been using files since the invention of the computers. Okay, starting from the magnetic disk, or if you like to see it that way, starting from the punch cards from 1800s, we have been using files. Okay, that's why I cannot cover all kinds of different file systems available. We are just looking different properties of file systems, and whatever is being used nowadays, or the ideas of file systems nowadays, we are trying to kind of look at those. Okay. One thing that we need to make a decision on is the block size. Remember the block size? Okay. What did we say? We keep our data on our disk using this logical block size. By the way, maybe I should show you this. Okay, this is how you organize your secondary storage if you are using disks. Okay, so disk means that, okay, you have platters, these circular plates, those are platters. Okay, I drill a hole in the center of them and I pass the spindle go through that. Okay, so this whole cylinder, this whole platter set spins this way. Okay, very, very fast. It's like 5,400 rotations per minute. We are talking about. Sometimes it is more than 10,000 rotations per minute, depending on your disk technology. It is very, very fast, and I store my data on these tracks, right? These are called tracks. Okay, so there are many tracks. There are many tracks on my desk. We are going to look at this structure when we come to the next chapter, which is I/O, input output. But for now, since we are talking about the files, I need to look at this structure before the time comes. Okay, so these tracks are divided into sectors. That's how the physical disk drives work. Okay, I have the platters. Okay, I have the tracks on the platters, and if you think that these tracks are connected, so they look like cylinders, right? So we call them cylinders. Okay, so this is a cylinder. If you think that these are all connected, and this is the read-write head mechanism. Okay, for each platter there is a read-write head for the upper side of the platter and the lower side of the platter, upper side of the platter and the lower side of the platter. okay, and the whole mechanism can move inwards and can go backwards, okay, to reach any desired track or cylinder. And if you combine these two movements, this head movement and the disk rotation movement, you can access, using this read write head, you can access any part of your disk that you like. Okay, that's the idea. But when you look at this structure, you don't see any places like the blocks. Okay, where are the blocks? We keep talking about the blocks, block sizes, the files are made of blocks, and etc. When you read a block, and we keep those kind of stuff, and you don't see any blocks in here, right? I don't show you any blocks. The reason for that you don't see any blocks is that blocks are logical things. They are not physical entities. They are logical entities. It depends on your file system how to interpret a block. Sometimes the file system says that I am going to take two sectors like this and call it a block. Sometimes it's going to be 4 of them, sometimes it's going to be 8 of them. So block is a logical entity, logical concept, and our whole file system depends on the blocks, not by the sectors. That's why it doesn't matter where my file system is. It could be on a mechanical disk drive, or it could be a solid state drive, right? So because I am based on the blocks, doesn't matter where I am sitting at, I am going to work as before as a file system. Okay, so let's go back and let's talk about the block. So the block size is a critical file system parameter, and it needs to be decided on. Okay, it needs to be decided on. So how? Okay, block size is restricted by the sector size, but again, it doesn't have to correspond to the sector size. I can use 2, 3, 4 sectors for each block. Okay, if I keep the block size too large, that means what? I have the problem of internal fragmentation. If I say that my block size is 1 megabyte, that means what? That is your minimum allocatable file size could be 1 megabyte. Okay, it's going to be 1 megabyte. What happens if I like to keep lots of 2 kilobytes long files? So each one is going to waste lots of this space. So if the allocation unit is too large, then it's a waste of space. If it is too small, just the opposite of it. So remember, for each block you need to keep for the bitmap version of the file allocation, you need to keep a bit, or for the linked list allocation, you need to keep a node, and etc. So it's going to be again waste of block space, waste of time. Why? Because if you have one megabyte file and your block size is 4 kilobytes, you are going to have hundreds of blocks in your file. So you need to keep this information somewhere, hundreds of blocks in your inodes, etc. That's going to be a waste of space. Also, you need to traverse all of those blocks to access all that information in your file, and that's going to be time. So there needs to be a trade-off. You cannot make it large, very, very large. You cannot make it very, very small. You need to find the balance. Okay, you need to find the balance. That's what we are going to look at. It's like very similar to page sizes in our memory, right? We had the same issue in there too. Okay, but again, this time, most of the time, since my file systems are based on the mechanical drives, okay, we still use the mechanical drives a lot. Maybe not our everyday computers like this, because for this one, power management is very, very crucial. With the power management, mechanical drives are not very good. So I use the solid state drives. Unfortunately, I don't have very large disk space on this computer, but I am okay because I am not using this computer to store lots of data. But for file servers, CPU servers, and that kind of stuff, they need lots of space. So they, instead of using the second solid state drives, they still use the mechanical drives. They are more reliable. They can store more data, and we have many advantages. So mechanical drives are still relevant in today's world. Okay, so let's look at this idea of how we can make this decision. Regarding the block size. One thing is that, okay, every day we have more need for the secondary storage. This table is nice, very old table, but it shows you kind of the tendency. The authors of this book, they say that they had this university system VU. In 1984, they have compared their file system, file statistics, file length statistics, and they compared it between this year, 1984, and 2005. Okay. In 1984, they say that almost 50% of their files are less than 1 kilobytes long. Okay. That's the idea, okay? Almost 50% of their files are less than 1 kilobytes long, but when the time comes to 2005, it is 30%. That means what? Our files are getting larger and larger. Okay, that's one thing. The other thing is for example, for a web server, doesn't matter what year it is. It has its own statistics. It says that although I am in 2010 or 2020, for my web server, the files are not that big. Most of the time, my web server files are very, very small. So that means what? It means, yes, my files are getting larger as the days go by. That depends on the current day, because I keep using larger and larger files, the multimedia files, video files, and the picture files, and etc. Okay, they are very, very large files. But the other thing is that for some applications, doesn't matter what kind of environment you are in. For some application, the files tend to be very small. What does that mean? It means that I need to have file system that can accommodate both. Okay, large files and the small files. Okay, it depends on your environment. So that means what I mean. You cannot say that 1 kilobyte long blocks are not relevant anymore to today's world. Yes, they can be, because if you have a web server, your files are going to be so. Maybe you are going to choose a small block size for your web server. For the other types of file servers, your block size is going to be larger. Again, it's a trade-off. So that's what we are going to. That's what we're going to do to consider this. There is a simple calculation here for the block size stuff. Let's say I have a disk. On my disk, each track is 1 megabytes. Okay, so it is 2 to the power 20. So per track, this track can hold, this track blue, maybe black. This track can hold 1 megabyte of data. Okay, our rotation time is 8.33 milliseconds. This whole disk can rotate. Okay, it rotates in 8.33 milliseconds. Okay, don't get this wrong. Okay, this disk rotates continuously. It doesn't stop. Okay, it just spins at this rate. Whenever you boot up your computer, your disk starts spinning. It never stops until you shut down your computer. Okay, so each rotation takes 8.33 milliseconds, and your average seek time is 5 milliseconds. What does that mean? Usually moving this head from this location to the other side of the cylinder range or the track range will take, for example, 10 milliseconds. But on the average, you don't do this traversal all the time, okay? On the average, you either go 1, 2, 3, 4, 5, or maybe half of this distance. So on the average, this says that, okay, I am going to take 5 milliseconds to move my head to the desired track, okay? So then we have the other thing. The time in milliseconds to read a block of k bytes is then sum of the seek and rotational delay and the transfer time. So let's look at this calculation. 5 is the seek time, 5 milliseconds. And then I have this 4165. It is half of this one. So on the average, to find your data on your desk, you don't have to wait your complete rotation of the thing. On the average, you are going to wait half of the rotation time. So half of the rotation time is 8.33 over 2, which is this one. So I did the seek time. This is the seek time. This is the rotational delay. And this is the transfer time. Remember, to read 1 megabyte of data, you need this much time, 8.33, right? But the thing is that I need to read k bytes. So I need to divide this k over 220, 2 to the power 2, because I am not going to read the whole thing, right? I am going to read only this portion of it and multiply it with this much. And the whole time will be my file or the data access time. Okay, my data access time. Okay, so let's look at this one. Okay, it's a read a block of k bytes. Read a block of k bytes. So let's try to put in some k numbers in it, and let's see what kind of read speeds we have in this graph. Okay, so you just read this graph, and I am going to do this. Okay, this is directly from the book. Yeşim burada mısın? Senanur. Salih burada mısın? Necdet. I am sorry to call out your names like this, but Hatice. Ahmet Tuğkan. Doğu Cem. So what are the possibilities that I am reading 10 people's name and they are all here? Okan Torun. Okay, good. So let's look at this picture now. The picture is this, okay? On one, it's kind of a confusing, but when you look at it carefully, it's okay. Data rate and disk space utilization. Let's look at the disk space utilization, okay? The dash curve, okay, left, okay, let's look at the right. The solid curve, right-hand scale. So let me try to colorize it. This is my blue one. The blue one is shown here. So this space utilization. So in my file system, all the files are all 4 kilobytes long. Okay, my files are 4 kilobytes. That's it. Okay, if your files are 4 kilobytes each, and if you're, by the way, this is the block size. Okay, if your files are 4 kilobytes each, okay, and if your block size is 1 kilobyte, that means that for each file you need 4 blocks, right? You are not wasting any space. Or for 2 blocks, okay, for 2 kilobyte blocks, you are not wasting any space either. For 4 kilobytes, that's nice because each file is just 1 block. No internal fragmentation. That's nice. But if you say my blocks are 16 kilobytes, then that means what? For each 4 kilobyte file, you are going to waste 75% of each, right? 75% of each block. That's going to give you 25% disk space utilization. Okay, so with the 4 kilobyte files and varying block sizes, okay, this blue curve that I have drawn is going to show you your disk space utilization, utilization. Okay, that's it. The other thing is, let's look at the other side of the picture. It's going to be this green stuff, like this one, and it's going to be the data rate. If I put in this formula here, okay, to read a block, what you need to do, okay, this is what you need to do, right? To read a block, you need to do this 9 milliseconds. So let's write it again. So this is almost 9 milliseconds plus K over 1 megabytes times 8, right? That's the formula, okay? When your K gets larger, okay, your data rate is going to be large. So for your data rate, because when your block is large, when you reach the block, you just read the whole thing. Okay, you just read the whole thing. That's going to be large. That's going to be good. So your data rate is going to be large for the large block sizes, and your data rate is going to be small for the small block size. Again, this is a trade-off. So what you're gonna choose is, okay, this is, by the way, this is for the files of 4 kilobytes. So if you have a web server, that's going to be nice, good. But if you have something different, for example, if you are serving big data stuff on your file server, maybe your block sizes should be large, because this assumption of your average block file size are 4 kilobytes is not a good thing. Again, you try to make your decisions like that, and usually when you set up your file system, operating system will ask you what kind of block sizes do you want. You can specify it, or if you like, I think you can. Do I have my disk stuff in here? Do you guys see any disk utilities? I think I had one. This disk, something disk. I forgot the name of that utility. That utility gave me all the parameters of my disk stuff. No, this is not. No, it's not giving me anything. What?
The second one was in the search.
Second row? Which one? This one?
When you searched.
When I make a search,
yes.
When I say disk, which one?
Hocam başlata sağ tıklarsanız orada var. Sağ. Bak.
Which one?
Başlata sağ tıklarsanız hocam.
Maybe this one? Yeah, it looks like these are my partitions. Is that true? Now this 0, okay, these are all NTFS. And let's look at this one. Yeah, these are some recovery stuff. These are for the BIOS stuff, and okay, this again the recovery stuff. Let's look at this one. Can I look at the properties of it? No, it is giving me the regular. It didn't give me. No, it didn't. It didn't give me. Okay, if you look hard enough, okay, if you look hard enough, you are going to see what kind of block sizes we have in it. I think this is, yeah, I think that was it. This gives me, no, it's not. It's giving me what kind of files I am, what kind of size I am using for each of my directories. No. Anyway, if you look hard enough, you are going to see what kind of block size you had chosen to format your disk. Usually it is defaulted to something and you don't change it, but it is in your hands to change these block sizes for your file system. Okay, so that's good. Any questions so far? I think I need to take a break. Our breaks are still 15 minutes. So we'll be here around 11:40. 11:40.
Hocam. İmzalamışım da ben.
Ne zaman geldin?
10 dakika sonra geldim.
10 dakika, yarım saat oldu buraya geçeri ya.
Yok, ben
Arkadaşlar
bu
zamanında girin ya. Benim adım okuladım da Yok, hepsini açmadım. Tamam, sen kara listedesin. Merak etme.
İmzalayamaz mı? 10
Yok,
dakika.
oradan oraya inmesi yarım saat sürdü.
Ben 10 dakika sonra geldim, oraya oturdum.
Zamanında girin arkadaşlar ya. Geldiğiniz zaman da şu tarafa doğru oturun. Herkes 10 dakika geç gelmiş. 10 dakika geç gelenleri imza atmıyor.
Hocam make-up'la ilgili duyuruyu kimse mi yapacak?
Make-up hala bana bu
Dilekçe geliyor.
dekanlıkla şey geliyor. Buna make-up yapın, buna make-up yapın. Bunlar bir biriksin de hepsinizi söyleyeceğim. Tamam.
Hocam ben çok limitliyim de.
He?
Yoklamadı.
Tamam, olmasaydı. Sinan Hocam bir şey sorabilir miyim?
Dersle ilgili.
Bu yazar. Şöyle. Bu iki farklı file sistemin herhangi bir tanesi mi oluyor bu sistemde?
Şey tamam.
Yok ya, olur mu? Çünkü ben Unix'te bir tane USB formatla da geçiyorum.
Herkes öyle diyor. Ve kaç sene oldu? Benim sınıflar. Çok iyi. Kestirdim de ben bayağı. Görünce bir saygı görünüyor. Daha gördü de aslında. Daha gördü değil daha dökülüyor ya. Güzel bir çok güçlü yaşıyor. Başka taşıyamaz hiç. Evet, bu yüzden öğretim de olmaz. Mesela hangi öğretim? Kahve değil. Evde kurdu. Ben de. Bak, şimdi bu çalışacak. Ben sistem bilmiyorum da. Sistem kaçtı yani bende. Bunu çalışan çalışmıyor. Çok böyle. Dışarıda pek bir işim gücüm yok ya. Neden çalışmıyorsun? İlla sıçması lazım. Ödev versene abi, en azından çalışmıyor. Ödev ne varsa onu çalışıyorsun. Aynen, size ödev versin. Çok güzel anlatıyor, gidiyor ödev. Ödev nasıl? Ödev mi var? Ödev var mı? Bir tane de var. Doğru. Yaptım ben rahatsızım demo göre. Hastaneye gitmiştim. Yarasalıkları olduğum onlarla görüldü aslında. Benim var değil mi? Bizim işte falan öğrenci kalkmıyor. Konuşuyor. Çok kötü ben ağzımda dilim üstünde konuştukça konuşamıyorum. Ağzıma gereken doktoru derdim yanlış. Rapor verdi yani de. Ama yani görüldü. Bir kere daha o çok yoğunsa eğer demo yaptıklarını yaptıysa çok fazla kalıyor. İnsanlar rahat da olmuyor. Unutmuştum ben böyle. Öyle tekrar belki. Yani çünkü 2 tane konuşmuştum. Böyle çok kısıt. Ben de şey mi yaptım? Böyle ilk evlilikte eksik yüklenmeyi yaptım. Aynen işte düşük vereceğim diğer şey. Belki daha iyi yaptım. Bir dahaki sonra bile bir dahaki öyle gelince yani. Başka bir güvenler var. Bilmiyorum işte. Sonra daha da bir nokta verdik. Şey yani burada kayıtlıyım ama bir geldiğim için mesela bugün gideceğim yerlere gideceğim. Bir gün kalıyor diyorum. Bir gün kalmak için. Bir gün kalmak için yapıyorum. Evet. Bir senenin başında yapıyorum. Ama artık bir güne dönüştü yani. Evet. Geçen de demiştim ki 2 ay kalmıştım. Sonra derslerim onlara döndü yani. Bu dönem öyle. Bayağı geç kalmam. Madem benim bilgi kaldı. Bir tarafa sanırım. Evet. Değişiklik oluyor. Bilmedim ben. Biz online olarak mı? Yok. Geldi mi? Öyle. Artık sen de şeyde kalıyorsun. Sen buraya taşıyorsun. Bayağı da yakın ya. Hangi gidiyor? Aynen. Ama muhtemelen farklı yerlerde. Şey, Beşiktaş'ta çok saçma oluyor. Otobüs ya böyle geliyor tekrar aynı yere gidiyor. Çok garip olmuşlar. Ben asla bu güzel dönümleri anlayamadım. İlk gün hatta yanlış ben Bayramoğlu'na gitmiştim. Aynen ilk gün o ada kısmına yanlışla gidiyor. Güzel orası da. Yani güzel ya. Benim güzel. Ben de gitmedim. Bayramoğlu sadece. İşte otobüste bir kere gitmiştim. Denizi görmüştüm yani. Ya o plajı, karşıda halk plajı. Oraya gitmesi değil. Yani böyle şey. Bir tane koy var orada. Çok uzun, çok geniş bir körfez gibi şöyle bir şey. Adanın şekli bir şey uçuyor, çıkıyor. Şey gibi işte. Ayrıca da öyle değil mi? Hemen sonra göstereceğim. Ben şurada yaşıyorum. Tam uçta. Şurada evet. Şurada. Şurada. Buradan ince sokarak koyunca böyle şu sahip koy. Denize giriyor ama gittikçe karanlık. Burası sahip. İlaç şurada bir yerde. Yani bak şuradan itibaren. Bak burası şuradan şuraya kadar şey. İlaç bundan sonrası sahip. Aynı zamanda.
10 dakika geç gelmişler diyor ki buradan buraya gelmesi yarım saat sürüyor.
Yazın artar mı acaba? Daha yazın bu da gördüm. Muhtemelen burası çok yüzde kalmış. Ve keşfedememişler. İstanbul sahilinde falan çok yani açık yani. Ne alaka yani? Hakikaten gitmen lazım.
Orada mısın? Çantanın içinde mi?
Yani. Hadi da burası çok kolay.
Kamera var.
Umarım yok. Şu an seni izleyemiyorum. Bir şey olmadı ya. Anladım sen.
Sigara falan geldi.
Bu dönemde zordu. Her dersten 8'den zordu.
8 falan mı? Sabah 8 yapmıyor.
Yapmıştım geçen sene ya. İkincisinde bu sene yaptım. Hatta şu anda bir ara staj yapıyorum. Orada yazmıyor.
Harbiden de ses ediyor.
Yazıda değil. İsmini bile unuttum ve küçük bir yazılım firmasıydı. Bayağı babamın tanıdığım tarzıydı. Cispa zor oluyor. Herkes dönmüyor.
Var fazla toplantı. Samet yok da.
Aynen böyle düşünüyorum.
Seninle ben konuştum seninle. Dedi ki o konuda çok bilmiyorum dedi. Ama devrimi kurarsak ya. Oradan da işte. Devrimi çalın.
Allah Allah.
Belki mail adresine bakıyorum.
Daha yok dediğin yere ait.
Aynen öyle.
Bütün fonksiyon ismi yazması olsa yapılır.
Bırakalım yani.
9 hakkım varmış abi.
Fazla okuyorlar. Tamam yeter abi. Böyle diyor zaten. Şu an bu sefer aldım. Şey, tablo altta var. Altta var. Kârı var. Yarın da Tabii orada bir Yok ya. Sistemde var mı? O zaman ülkemiz aslında ben bize falan sahip oluşan çıkardı. Herkes bunu aldı.
Okay. Another issue that often comes up is these quotas. Usually, if you have a multi-user system, you like to okay. Are we okay now? Can we start? Usually, if you have a multi-user system, you like to limit each of your users in terms of how much disk space they can use. And you need to enforce these rules because, I mean, remember, one of the purposes of the operating systems is to manage the resources and be fair among the users and the processes. And you like to say that, okay, this is enough for you. You cannot use more than this much of this space. And these are called disk quotas. And these quotas could be in terms of the number of bytes that you are using or number of nodes that you are using, inodes in terms of, or the number of files that you are using. These are all could be your quota related restrictions. Okay, there are two types of quotas. One is the soft limit. Okay, soft limit can be exceeded, but the hard limit may not. Okay, two types of quotas, the soft quota and the hard quota. When you exceed the soft limit, soft quota, you get a warning message saying that you are using too much disk space. But the operating system will never let you use more than the hard limit size, because that's the hard limit by definition. Okay, again, this quota doesn't have to be in terms of file sizes or the total disk space. It could be either the number of files or the for example, you are a user that use lots of inodes. Okay, using lots of inodes means that you are opening too many. You are creating too many files. Those are very small files. You don't use up much disk space, but you are using lots of inodes, and inodes are resources. So you may be limited by the number of inodes that you are using. So let's look at how we can enforce these quota restrictions. This is what happens when you open a file. Remember, we keep our open files by a pointer in our process table. Okay, this process is opening these files. Okay, and that's the open file. And the open file in my file descriptor table, I have a pointer to a quota table. Okay, in that quota table, I have the soft block limit and hard block limit, and the current number of blocks and the number of blocks running, and etc. I have all these kind of information. Okay, so all the files opened by this process will point to the same quota table. So whenever you added a new block to your files, you increase, okay, you increase the current number of blocks, okay, and you decrease the number of blocks warning left and etc. Okay, doesn't matter how many files you are opening, at the same time the same file. Since they are all pointing to the same quota table, they will update the same table for that user. If you have a file, okay, I have a file, and it is writable by everybody. If somebody else opens my file and appends the data to that file, that means that user is using my quota because that file belongs to me, right? Okay, and this quota system should handle these kind of situations too. And this is how we handle stuff. Maybe you did not get much quota restriction messages from your operating system because we are using our personal computers, and in our personal computers, usually we are the first and only human user that uses the system. That's why it doesn't make any sense to restrict ourselves in terms of quotas. But if you are in a multi-user stuff, for example, if you receive too many emails with very large attachments for your GTU extension email account, you will hit your quota and you will get a warning message saying that you are using too much disk space for your email. So you need to delete some of your emails if you like to continue receiving emails. So for that system, definitely you have some quota problems if you receive or send too large files. Okay, another issue is the backups. Okay, again, the data that you keep on your secondary storage is supposed to last long. You are not supposed to lose it after each power up, power down, right? So that data is valuable. You need to keep it stable. You need to keep it valid all the time. So one way of keeping that data in a valid state is taking regular backups. Okay, make a copy of your whole file system from time to time, and that will be a good solution. That's what we can do. Those are called file system backups. Okay, and when you are doing the backups, of course, when I say make a copy of your whole drive, and some people say that, why do we have to take the backup of your temporary files? Because as the name implies, those are temporary files. I just open it temporarily to keep some temporary data, and whenever I am done, it just sits there. I didn't delete it. Okay, so I don't have to take backups of the temporary files or the /dev files. /dev files are the device files. Okay, your device drivers. Okay, they don't change. Okay, you don't have to take because they belong to the operating system. Okay, they are part of the operating system. Those are not my personal data, so I am not going to take backups of those. So no need to back up all the files. Maybe we should be smart about it. And if I keep taking backups of the whole system, let's say every week, I don't have to take the backups of the unmodified files because I did not modify them. I already have a backup of it. Okay, the unchanged files need not be backed up. Okay, another nice idea would be compression during the backup. While you are taking the backup, compress your data because most of my disk data can be compressible, such as the text data, and these are kind of the things that you need to be careful about. Other things are these two things. It is very difficult to take a backup of an active system. I am working on my system. I keep changing my data on my system, and I am trying to take a backup of it. So that would be a dangerous thing because why? At the beginning of your backup process, let's say your backup process is going to take half an hour, but you are still modifying your disk. Okay, you are accessing your files, you are modifying them. So when you end when you finish your backing up process, the data at the beginning might be very different than the data at the end. So you may end up taking an unstable version of your system. That will be a problem you need to be careful about. The other thing is that security problems with backup. Where do you keep your backup data? I mean, if it should be in a safe place. Otherwise, as the name says, it is backup. It's copy of your data. Whoever has access to that data has access to all of your information, and you need to be careful about it. So most of the stuff, like taking the snapshots and the security problems, the compressing, I will not talk about them. Maybe I will talk about these two. As I said before, file systems are very complicated. We have been using the file systems since the punch card days. So more than 100 years of issues and the solutions and etc. There is no way that I can look at all of those issues. So I am trying to kind of look at what are the relevant stuff today's computing world. Okay, let's look at this file system backup strategies. Two types of strategies we are going to use. One is the physical dump. The other one is the logical dump. Physical dump is the most straightforward version. No logic is involved in it. Everything is very simple. It just says that if you have a disk like this, okay, this one has your data, valuable data. Take another physical disk, which is exactly the same disk, and copy everything to this place. Okay, so that's going to be copy track 1 to track 1, track 2 to track 2, track 3 to track 3. That's it. Okay, so it is just starts from the block 0 of the disk, write all the disk blocks onto the output disk in order. Okay, so remember what we said about why are we taking the backups of temporary files? This one doesn't care. Or this one is so stupid, okay? It takes backups of unused spaces too, okay? If your disk is 50% full, it just takes a backup of the unused space. So it is just copying the garbage data too, okay? So that's the cost of having a very simple algorithm, right? Just copy everything, copy all the blocks to another disk. Doesn't matter what kind of data it contains. Even if it doesn't contain any data, it just creates it, okay? The other thing is that, okay, unused disk spaces, they are just backed up. Bad blocks, okay? These are mechanical stuff, physical stuff. From time to time, some of these sectors will go bad, okay? An operating system marks this sector as a bad sector. It will say that this sector is bad. I am not going to store any data on it. Why is it bad? Because whatever I am writing to it, I cannot read it back. Okay, that's what you do when you are writing to this sector, okay? You write to that sector. If you cannot read the same thing back just after writing, that means that that sector is bad. Okay, so I mark it as bad. This physical dump strategy doesn't care about the bad sectors. It just takes a backup of it too. Okay, that's another disadvantage of. Okay, so physical dumps. So physical dumps are fast but unable to skip selected directories, make incremental dumps, and restore individual files upon request. So these are the downsides. So what are we going to do? Let's look at this logical dump stuff. The logical dump says that, okay, I will be careful, I will be smart. First, I will ask the user where should I start my backup process, the directory. Okay, it says that it starts one or more specified directories and recursively iterates, traverses all the files and directories underneath, and it just takes backups of, okay, all the directories, okay, that lie on the path to a modified file directory. Okay, so this is a much better backup strategy than the physical one, but of course it is more involved. And the advantage is it will make it possible to incrementally restore a single file. When you take a backup, okay, with the physical backups, if there is a problem with your data, let's say I like to restore it, load it back from your second storage to the second disk to the first disk, you need to load everything back to this one. Okay, no partial restoration is possible. With the logical dumps, it is possible. Okay, I can restore a single file. I can restore a file depending on your time and etc. Okay, these are the advantages of these logical dumps. Let's see one example of the logical dump picture. Let's say this is my file system, and I say that, okay, of course, like before, these squares are the directories, the ovals are the regular files. If a file is shaded, this is a modified file, unmodified directory, modified file. Okay, it looks like that. Okay, so this file is modified, this directory is modified. So the physical dump will take backup of all the blocks here, okay, all the files and directories. Doesn't matter if it is modified or not. But with the logical backup strategy, you don't do that. Let's see what happens with this stuff. Okay. Phase 1. For each modified file, its inode is marked in the bitmap. Okay. For each modified file, these are the modified file, their inodes are marked. Are saying that, okay, these files are modified, so I am going to mark their inodes. I am going to take backups of those inodes. Okay. Each directory is also marked with each directory is also marked whether it is modified or not. So first I mark all of these files inodes, and then I mark the inodes of those directories. All the directories, doesn't matter if the directory is modified or not. Okay, so that will be the picture here. Okay, so that's the first. So 3 is marked. See, 3 is marked in this bitmap, and 8 is marked. 9 is marked. 9 is marked, right? So all the files that are modified are marked. Also, all the directories are marked. So 1, 2, 5, 16, 18, 27, they are all marked. Okay, that's how the algorithm begins. And then the second phase, I walk to 3 again, the 3. Okay, I look to this 3 again. I unmark any directories that have no modified files or directories in them. So we go back and we say, okay, we say that in the second phase, for example, this 10 and 11 and 14, they don't have any modified files in them in any path. So I am going to remove. So 10, 11, 14, and where is 15? 15 is a file name, okay? So they are removed. So if you like to see it that way, this A and B, these two first steps are doing this. They mark all the files, modified files. Also, they mark all the directories that contain any modified directories or files in their path. 1 is marked because it contains this 3, okay, inside its path. Also 2 is marked because it contains 3. 5 is marked because of these 2. 6 is marked because of these 2. 10 is not marked, or 11 or 14 is not marked. Okay, well, I need to mark these because 1, 5, 6, because of the incremental restoration. When you say restore this file 8, that's going to affect all the directories inside the contained in the paths or this 8 and 9. Okay, so that's what I did, A and B, these two steps, 1 and 2. The third one is scan the inodes in numerical order. Remember the inodes? Remember, if we have an inode based system, inodes are kept in a special place in my partition table. Okay, file system partition. I scan the inodes in numerical order and take backups of all those inodes. Okay, so first I take the backups of inodes that belong to these marked files and directories. Okay, and after that the files marked are also dumped, again prefixed by their attributes. So after the inodes are pointing to blocks, and I put the blocks back to the backup place. Okay, those are the well, these two are actually one step maybe. Okay, those are the main three steps of taking a backup of incremental backup or the logical backup of a Unix based file system. Okay, so first mark all the files and directories that needs to be backed up, then write their inodes to the disk, to the backup disk, and write their blocks to the backup disk. Okay, well, simple enough. Well, it is not as simple as copy everything to the other disk. This one needs to traverse all this tree, and that's why it can say things like, I am not going to take backup of this temp directory, I am not going to take backup of the dev directory, and I am not going to take backups of these unmodified files, right? How do you detect the unmodified file and detect files? How do you make that decision? Question for you. How do you say that 15 is not modified and 9 is modified? Yes.
File attributes.
You look at the file attributes and you know your last time you take a backup, right? You compare them, right? That's it. Okay. The physical backups, okay, physical dumps, they don't care. Because physical backups, they don't care about your file system. Okay? They don't care about your file system. They just block by block, it just copies them, whether it contains useful information, not useful information. It is fast, it is easy, but it is wasteful in terms of system time and resources. Okay, good. We talked about this. Good. Any questions? Another issue that often comes up with the file system is the file system consistency. Doesn't matter how careful you are in terms of using your journaling file systems or taking your backups and that kind of stuff, from time to time, whether because you have file system bugs in your operating system, physical problems, electronic problems, mechanical problems, okay, your system will be inconsistent from time to time. Okay, your system will be inconsistent from time to time, and I can do some stuff to at least help with this inconsistency. Okay, and the operating systems offer utilities to check for system consistencies. Okay, Windows has this system file check, and this is a file check system or something like that for the Unix. Okay, each operating system, depending on the file system that you are using, offers such utilities. You run these utilities from time to time, making sure that your system at least consistent with respect to some criteria, and we are going to look at that one. For example, we like to be very careful about these inode blocks. They have to be consistent. What do I mean by consistency? It is this. Okay, it is this. Let's look at the consistency check algorithm, and we are going to see why we are calling it consistency. By the way, when you run your system consistency checks, that doesn't mean that you solved all of your problems. There are certain problems that we are trying to address, and that's what we are going to look at it. Okay, so when you run this program, file system file check, fs check, okay, file system check. When you run this program, it keeps two tables, okay? It keeps two tables. One containing a counter for each block, initially set to 0, okay? So two tables like this. Table number 1 and table number 2. Each one will contain the number of entries in each table is the number of blocks on your whole system. Okay, let's say I have total of 15 blocks on my file system, which is a very small number, but that's a simple example. And I am going to keep two tables of size 16 and 16 here. Okay, this one will, for block number 0, okay, these two numbers, okay, will represent how many times I have seen this block in a file. Okay, I will scan all the files. Let's say file a.txt. When I scan this file a.txt, all the blocks that file a.txt uses will be marked like this. Okay, remember at the beginning these counts are all 0. It says that file a.txt uses this block and this block and this block, right? Then I do the same thing with the file B and file C, and for all the files, I increment these values by 1. Okay, I increment this by 1. For some reason, I don't know why, let's say file d.exe says that I am using block number 72, so I will increment, again it is 2. Well, it shouldn't happen. I mean, a block belongs to a file only. Two files, if they are not using any linking and that kind of stuff, cannot use the same block, inode or the regular block, right? But I mean, the reason why we are using this is the system consistency, right? Check file system consistency. This is definitely a problem, okay? We are trying to solve that problem. So this first table keeps the count of the blocks in use by different files. The second table checks the free block list, okay? In my file system, I have to keep track of the free blocks, right? And free blocks are usually kept either using a bitmap file like this. These are the free blocks. You say that in my system I have a total of 1 million blocks, and these are the free ones. Okay, this is a bitmap solution, and this is again, like we did many times before, this is the linked list solution. This one says that block number 42, 138, 210, 97, these are all free blocks. Okay, so I have a free block list, linked list, or the bitmap. I scan this list, or I scan this bitmap, and I mark all the free blocks one by one. Okay, and at the end I expect such a nice configuration. A block is either in use or free. Okay, in this case it is in use, free, in use, free, in use, like that. Okay, so I like this picture. There is no inconsistency in this file system. Each block is either in use or it's free. Okay, so in this case, this Unix utility file system check, okay, this Unix utility file system check, it says that after running 2 hours, it's going to tell you that I ran and I checked all the blocks and they are consistent. I can't do anything for you. You are fine. Okay, you are fine. You are consistent in terms of block usages, whether they are inode blocks or the regular blocks, doesn't matter. Okay, if you are not that lucky, if something happened in your system, you don't know why it happened, you don't know how it happened, but it happened. Okay, you may end up having a picture like this. What is the problem with this picture? Say it louder. You mean the block number 2? Yeah. Block number 2 says that nobody uses block number 2, but it is not in my free list either. Okay. This is inconsistent. Okay. I mean, it has to, a block has to be either free or it is occupied, right? You cannot say it is not both. So this is what? This is waste of space, right? So how would you solve this problem? How would you solve this problem? You may ignore it. You are saying that, well, I mean, I am not losing any data. Some block is not used at all, so I have enough space. That might be one solution. Or the other solution could be, which is the better one, could be just add block number 2 to the free block list, right? Just add block number 2 to the free block list. So you just go to this, picture and block number 0, block number 1, and block number 2, just make it available. Okay? Or at the end of this list, put 2 in here. Okay? So it is available now. It is more consistent. You might say that, well, maybe we are hurting something. Maybe some file is damaged and I am using that space as a free, but I mean, you cannot do better than that because nobody claimed that block to be part of that file. I mean, the one theory here, remember our log file, journaling file system? With the journaling file system, remember how you remove a file? You remove the file name, but before you remove the inodes and the blocks of that file, the system has crashed. Maybe this has happened because of that. You removed the file name, system has crashed. You didn't have chance to free the inodes and the blocks of that file. So nobody uses those blocks, nobody uses those inodes, but they are not in the free list either. So it might be a reason like that. Okay. So I solved this problem. So that's one case. Let's look at the other case. Let's see this picture. What is the problem with this picture? Yeah, block number 4, it says that block number 4 appears 2 times in my free list, right? Block number 4 appears 2 times in my free list. That's not good. Okay, so what would you do? You go to your, well, for example, first of all, this cannot happen with the bitmap free list representation, right? With the bitmap free list representation, there is only 1 bit for the block number 4. But for the linked list representation, it looks like this number 4 appears 2 times in my linked list. Find the second one and delete it from my linked list. That would be your solution, right? That would be the solution. So we kind of solved this problem too. And let's look at this one. Oh, this is kind of weird. 2 different files say that I own this block, I use this block. This should not happen, right? This should not happen. I mean, there is definitely something is hurt. How would you, I mean, you are hurt anyways. 2 files are sharing the same block. They shouldn't. This is not linking the related stuff, okay? So how would you solve this problem?
Cancel one of them.
What?
Cancel one of them.
Cancel one of them, but what's going to happen to your data? Yeah.
Copy one of the data to another premium.
Yeah. Take these 2 files, file A and file B, right? They say that they are both using the block number 5. You cannot, they say. Okay, so what are we going to do? Make a copy of this block number 5. For example, use 14 for that one. So you tell file B that you are not using block 5 anymore. You are using block 14. So make this one, Now file B is using block number 14 because I copied this 5 to 14. And now file A and file B, they are using distinct blocks from now on. Okay, I kind of solved it. I mean, well, these are not perfect solutions, but I kind of solved it. And at the end, running these file system check utilities, you report all of these stuff to the user. You are saying that, okay, if you have run these utilities, Unix does it from time to time. When you boot up your computer, it says that last time you shut down your computer, it wasn't a proper shutdown. I am running this file system check. I have discovered this many unused blocks. I took backups of them. I made them available. Remember those? It says that I have took backups of these blocks, and without, I mean, it doesn't do this automatically. It says that I am taking a backup of this block number 2, and it is now available. Okay, so it takes a backup of it. This block number 2, it just doesn't make it just 1. Okay, it takes a backup of it to in a file, and then it makes it 1. After that, and it reports all of these. It reports this one, and it reports this one, and it reports this one. Okay, all file systems have these kind of utilities to check the file system consistency. I am not saying that it solves all the problems, but at least, I mean, my picture should look like this. I cannot ignore this problem or this problem or that problem. Good. Any questions so far? Good. Okay, let me continue then if there are no questions. Okay, we said that file system performance, it depends on the cache a lot. There is a cache, of course, that says CPU. This is my memory, and this is my controller, and this controller is connected to my desk, right? And this is my system bus. Okay, usually we keep some part of our memory for the what happened? My pen stopped working. Okay, usually we keep some part of our memory as a cache between the disk and the CPU. Okay, sometimes this cache is inside this controller, sometimes inside the memory. Okay, definitely there is a cache inside my controller, as I said before. Okay, so how do I manage this cache? Remember how we did the page replacement algorithms? There was a very nice page replacement algorithm which was the least recently used. You replace the least recently used part of your memory, okay? But we could not implement this least recently used because least recently used algorithm requires either a specialized hardware. Okay, that specialized hardware always keeps tracks of which pages are least recently used. It just keeps incrementing the timestamp of the pages of the last access. We said that if there is no hardware help, I cannot do this by CPU because it is too much time. For the disk caches, I can do that. Why? Because for the disk world, accessing the disk and loading the data back and making the replacement takes a very, very long time. So instead of spending that much time for disk access, maybe I can spend a little bit time to update this time of last access to a disk location. So implement the LRU, okay, least recently used algorithm. Okay, so I can directly use this LRU algorithm to implement it very, very efficiently. We like the LRU anyways. But the thing is that LRU is not always the best solution for all the what should I say, for all the blocks that we are using. For example, I know when you open a file, right? what do you do? The first, you load the inode first, right? Inode contains the indexes of the blocks. I know this one. LRU. We say that I'm going to load the inode first. So I know that I access the inode. I am keeping it in that memory as the open file, and I know that I will never read the inode again because I have loaded to my memory. I am keeping it there. So maybe I should not put this inode through this LRU algorithm, because LRU will say that let's keep the inode block in my cache. No, don't keep it in my cache, because I have loaded that inode in my memory. I will keep it in my memory in my user program, and I will never access that inode again because it is in my memory. So let's keep an exception for this inode. Okay. I am not going to read it again. It is essential. It's very critical file, but I am not going to read it again until I close this file. So don't run LRU for this kind of stuff. The other one is this, okay? Sometimes if the node is very critical, don't keep it in the cache, okay? Whenever it is modified, always write it back, okay? So don't keep it in the cache. Whenever it is modified, always write it back. And this might be another exception case. Okay, I think I will stop at this point, and tomorrow I think I will finish up with this chapter, and I will start talking about the input-output chapter. Okay, read the chapter and until the end of this chapter for tomorrow, and come to class like that. Okay, see you tomorrow.